Hello, my name is Benedicton Kaskan, and if you like to call me, call Kaskan direct. And I'm going to express you some sort of things that mostly is concerned with chemistry and also in biology. But what aspect most represents about answering different questions and derivations of the different calculations respect to the chemistry and the biology. And what are things I want from you is about subscribe, share, comment. What are things I'm going to share to you? I know that this is the idea that I have, so we must share our knowledge, our skills. Also, in a part of attitudes, I know yourself, maybe you gain some of the things, maybe you're being shy with others. It will made you to be in such case for attitudes good to answer, can trust others in such case. So, if you have tried to use, and if you haven't tried to transfer, in order to gain it, in order to reach some aspect of life and how it being seems like. So yourself, you can reject different aspects without now the real cases, without describing the different aspects that made you to fail reaching certain goals. I know most of the things are more people are going to fail on this world is others of the door side on our side can make them to gain their ends that they are keeping in our mind. So, what are things I want to try to you is that reback on rain that for today, what are things I prepare for you is about all the aspects that's concerned with chemical reactions. I know that any chemical reaction not to occur, it influences with the different kind of factors. And among the factors of data we're going to describe is about temperature from others by concentrations. There is catalyst, there is rate, there is nature or physical properties of the reactants or products of the reactants normal and others. So for today, we're going to look on the effect of temperature in part of activation energy and the rate constant and how it's being affected from the chemical reactions or during chemical reactions. So the thing that we're going to do today is about the relationship. We're going to look about the relationship between temperature, activation energy, and what called rate constant by Arrhenius equation. So direct from that, if we're going to describe about the relationship between temperature, activation energy, and reaction constant, we're going to describe from these equations for Arrhenius, that is rate constant of chemical reactions is direct proportion to rho inverse of negative activation energy over RT. So to remove this proportion, it will be rate constant is equal to Arrhenius constant times rho inverse of negative EA over RT. So from that, this is the Arrhenius equations. But as you see here, we're having those categories that we're going to describe about how it's separated from the equations by looking about rate constant, activation energy, and and temperature. You see, so we're going to look at this aspect, and this aspect. But by looking here, by describing here, we can see that this rate constant is inverse proportional to temperature. So rate constant is inverse proportional to temperature. but the rate constant is equal to kinetic energy. You see? So from these relations, Rayleigh look on the different aspect on how it is separated by correlating the two equations. Maybe that the count changes. So from that Rayleigh formulating the first equation, that is, it will be K equal to A negative EA over RT. This is the Arrhenius constant, and this is rate universal gas constant, and this is the absolute temperature, and this one is activation energy. So this is the universal gas constant, this is the absolute temperature, this is activation energy, this is Arrhenius constant, and this is rate constant. So from that, what are things we're going to verify as much? We're going to apply natural logarithm, that it will be rho k equal to rho of a. Since it is times, it will be plus according to mathematical rule. It will be plus rho of e negative power EA over RT. But I think to note that rho E is equal to 1. If you plug into a calculator, you will get this one answer. So it will be rho of K is equal to rho of A minus EA over RT rho E. You see? So from that on now, as I said that rho E is equal to 1. Rho E is equal to 1. So it will be rho K is equal to rho A minus EA over RT. So we can see that this is the equation 1 according to the natural logarithm. So we can apply either natural logarithm or common logarithms. But first of all, we must start with the natural logarithm, and after that we continue with the common logarithms. So from that, if you get the answer, this is the first equation, and the second equation will be rho K2 is equal to rho A minus EA over RT. Over RT. That is the equation 2. You see? So this is the temperature 2, and this is the temperature 1, and this one is the rate constant 1. So from that, I'm going to make a relation from these two equations, that it will be rho of A. It will be equal to rho of A. Since this the rho is a Arrhenius constant, it means that for the first equation and the second equation it will be similar. So from that we say that this one is equal to this one. So for the first equation, it means that when you say rho A, it will be for first equations, it will be K1, it will be rho K1, yes, plus EA over RT. This it is what? Equation 1. This it will be equation 1, and the equation 2, this equation 1. Equation 2 will be rho of A1 is equal to rho of K2 plus EA over RT2. This equation 2. You see? So from these two relations, it means that this one is being rated this one, and this one is rated with this one. So from these relations that are rated here above is this one. So from that, we'll jump again to the another aspect, that it will be rho run of k1 plus ea over r t1 is equal to run of k2 plus ea over r t2. You see, so from these two relationships we're going to correct the similar term or the same terms that is being rated under meanings. That's this k1 and k2. So it will be run k1. This one it will be jump to here this side. That it will be, this is plus. When cross through the equal sign, it will be negative run k2 is equal to, we tie this one, that will be ea activation energy over rt2, and this one is plus. It will go to jump to this side. See, so it will be minus activation energy over rt1. You see, so from that I'm going to continue with another equations according to the law of logarithms. When it's minus, it will get divided, so it will be run of k, it will be run of k1 over k2 is equal to activation energy over rt2 minus activation energy over rt1. So up here I'm going to factor out the value for activation energy and the universal gas constant. That will be run k1 over k2 is equal to activation energy over universal gas constant. That's up then remaining 1 over t2 minus 1 over t1. So this one we can see the relation that's direct up to the ends of the equations. You see, but we can rest by writing this one, that run of k1 over k2 is equal to activation energy over universal gas constant into bracket. Here it will be, we'll find the lowest common multiple, that is the temperature 2, temperature 1. So when you divide, we will get temperature 1 minus temperature 2. You see, so this the general equations of Arrhenius equation that show the relationship between activation energy and temperature when it is on change. So it means that when the temperature is changing, the Arrhenius equation you take maybe the initial to the finds, and at the end you get the equation. That equation is going to plug on or when you have given an equations or any questions about calculations, maybe the activation energy or the universal gas constant from the Arrhenius equations, and you have given two temperatures, you're going to use this formula. And for other things, I'm going to assist you with that. Try to consider the law of mathematics in terms of brackets in different aspects. Since when you're using your aspect on calculating the sum, it will be difficult to get the right answer. So make sure that you make your stations in a proper way in order to reach into consideration that your answer is in the correct way. So this is the aspect that show the relationship between temperature, activation energy, and the rate constant. And commonly this derivation is based on the natural logarithms. So read up again, look on the common logarithm. Common logarithm. How we can solve by using common logarithm, like they are all the same as the first one that I use the natural logarithms. But look this one. The first of all, you must formulate your normal natural logarithms. That is run k1 equal to equal to run of A plus run E negative E A over R T. You see? So if you formulate this natural logarithm, after that we're going to find the common logarithms. So plug into common logarithms, that should be log over log rho inverse of K1 is equal to log over log E of A plus, but this rho E is equal to 1. You see? So rho E equal to 1. So up to the end of answer, it will be minus activation NH over RT. You see? But this I use maybe for temperature 1, and this was a temperature 1. You see? So if you get the respect at the end, it will be, when you say 1 over log rho inverse, it will be equal to 2.303 when we were approximate. You see? So it means that the equation, it will be 2.303 log of K1 is equal to 2.303 A log of A minus activation NH over universal gas constant to temperature 1. So you get that equation. So up to the end, since we have this var, that is 2, and this is 2, so we're going to divide by each side. All right, so it will be 2.303, and here we divide by 2.303, sorry, 303. But this one will cancel with this one, and this one will cancel with this one. So up to the end, you will remain with log of K1 is equal to log of A minus EA over RT divide by 2.030. But up to the end, it will get this one, it will be log of K1, but this is the temperature one, right, is equal to log A minus EA over 2.303 RT1. You see? So this one will be equation 1. Alright, so for the equation 1 to review, log K1 is equal to log of A minus EA over 2.303 RT1, and for the equation 2 it will be log K2 is equal to log of A minus activation NH over 2.303 RT2. So here we're going to correct the same terms. Alright, we're going to correct the same terms. So now this one is equal to this one, and this one is equal to this one, and this one is equal to this one. So first of all, making subject of rho A, since rho A is constant, so we're going to make this constant. So it will be log of A is equal to log of K plus activation NH over 2.030 RT1. This is K1, and for K2 it will be log of A is equal to log of K2 plus activation NH over 2.0.303 RT2. So we say that this log A is equal to log A, and this one we say it is a constant, so it does not change. So what aspect we're going to consider is that we're going to take take log K1 plus activation NH over 2.303 RT1 is equal to log of K2 plus activation NH over 2.303 RT is RT2. So this is the relationship. So we're going to correct the similar terms. That's this one to go with this one, and this one it will be with this one. You see. So up the end we remain with the log K1 minus log of K2 is equal to the what? To the activation NH over 2.303 RT2 minus activation NH over 2.303 RT2. Up then, according to the law of logarithms, it will be log equal to K1 over K2 equal to, so here we factor out the variable that is constant from both sides. That will be EA over 2.303 R. So we factor out, it will remain 1 over T2 minus 1 over T1. So this one we say that you already derived it, but you can end up with this one. We say log K1 over K2 is equal to activation NH over 2.303 R into bracket. We're going to use lowest common multiple, that is will be T2 T1. So when we divide, we get T1 minus T2. So this it shows the relationship between the change of temperature, activation NH, and the variety constant. So it means that when you have given two temperature during the chemical reaction, it means that during the initial and up to the finals, or during the progress up to the finals, you use these equations maybe to find the activation NH. Since you here through this equation and from the equation maybe you have given, you may find the rate constant. Again, you may find the activation NH. Again, you may find also the universal gas constant, but even if it's constant, maybe you have given the rate constant already and activation energy already, both temperature you have given, so you find this universal gas constant. So it depends on the nature of the question that you have asked. So make sure that you have an ability of correlating these two similar terms. So you can verify that from the first equation by concluding this aspect. We say that log of K is equal to activation NH over RT is equal to 2.303 RT. You see? So this you can say that log K is equal to activation NH over 2.303 R, and this 1 over T. You see? But this is negative and this is negative. So from these relations we can conclude that the log constant is inverse proportions to temperature, and also deduct proportional to activation NH negative. You see? And also we can say that this in part of calculation, maybe using the graph method, you can derive these equations that log of k is equal to log of A plus activation NH, that's negative, over 2.303 RT, and this one will be reversed, that will be log k is equal to negative activation NH over 2.300 R 1 over T, and this one is plus log A. You see? So this is equal to y, and this is equal to slope, and this is equal to value of x, and this one is equal to c. You see? So from this you can derive the equations, means that when you get the part of slope from a graph, maybe you can get the value of negative. So make sure that you know about that aspect on how you can demonstrate, on how you can use it, and application on the solving different equations in chemistry. So what are things that I will say to you? Thank you very much indeed to listening to this, and I know that I will be together on another sessions. Thank you very much indeed.